Yeah, hello everyone. Myself Maruti welcoming you all to this physics video session. In this video, I'm going to talk about atomic structure. In that one, the quantum numbers, right? The main four quantum numbers are nothing but principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Right. In this video, I'm going to talk about magnetic quantum number. Right. So before that, what's a quantum number? Quantum number is telling about around the nucleus in an atom where the electron is, what is the position, what is it, in which state it is, in which direction it is moving, in which towards which axis it is oriented. All this stuff it is said by quantum numbers proposed by Erwin Schrödinger. Now we are talking about magnetic quantum number. What does a magnetic quantum number talk about? Is it talking about orbit? Is it talking about subshell? Or is it talking about orbitals? So mainly how to remember, magnetic quantum number is talking about orbitals in a subshell of an orbit. You have to remember, magnetic quantum number is talking about orbitals of a subshell in a orbit. That's good. Right, see here. Orientation of the orbital in the space around the nucleus in relation to the other orbitals in an atom is indicated by magnetic quantum number. I repeat, orientation. What's the meaning of orientation? Let me explain to you. Suppose if you take an x-axis, okay, if this is an x-axis, obviously this is the y, right, and this is the z-axis. This is x, this is y, and this is z. Right. Now, how the electron is oriented? Orientation. It's oriented along x-axis. Right. When we are talking about x-axis, obviously, in the right, it is in relation with the y, in relation with the z. That is nothing but they are perpendicular to each other. Right. How they are moving, how the electrons are moving, how it is oriented along the x-axis in relation with the other orbitals is explained by magnetic quantum number. Orientation means movement of the electrons, right, in accordance with any axis in relation with other axis, here y and z. That's what. So orientation of the orbital in the space around the nucleus in relation with the other orbitals in an atom is indicated by magnetic quantum number. That's magnetic quantum number. Who proposed this? It's nothing but Landé. So magnetic quantum number is proposed by Landé, and obviously every quantum number has its own symbol. Principal quantum number has N as symbol. Azimuthal quantum number has L as its symbol, and magnetic quantum number is symbolized by ML. Alright, as a subscript we are keeping L. Why did we keep L? That's very, very important. Why? Because magnetic quantum number is always dependent upon azimuthal quantum number. Right, that's what it is dependent on L value. So how many how many values does M has? Means obviously it depends upon L. How it is dependent? Let us study regarding that one. Suppose assume that we are considering a nucleus. Obviously, I am taking three orbits here, K, L, N. So for K, N is equal to 1. We know that. For L, N is equal to 2. And for M, N is equal to 3. Principal quantum number is 3. Now, suppose we know that the orbit which is away from the nucleus, right? Let me take the third orbit, that is M. It is having more energy. Right, we assume that an electron in the third orbit, right? Suppose if this is the excited state for that electron, excited state, right? It is in the excited state. You mean we know that an electron may not stay in an excited state for a long period, right? It goes back to its ground state. Now in this process, when an electron jumps from higher energy orbit to lower energy orbit, suppose the electron is here, it releases its energy in the form of electromagnetic radiation. Electromagnetic radiation, we know that, right? Now if you observe those electromagnetic radiation in an emission spectrum, right? Emission spectrum, If you observe that, right, if you observe those electromagnetic radiation in an emission spectrum, obviously, right, and now let me take, of course, let us take, this is for the K, right, this is for L, and wantedly I am taking M. Okay, right, of course, these are nothing but the line spectrum. Right, of course, these are indicated by principal quantum number. For this, n is equal to 1, this is n is equal to 2, now n is equal to 3. These are nothing but the line spectrum, right? These are denoted by principal quantum number, as we all know. Alright, now each orbit is going to split, right? Now as n is equal to 1, it is going to split into one line, and as n is equal to 2, it is going to have 2 subshells, and as n is equal to 3, it is going to have 3 subshells. Okay, these are nothing but the fine spectrum. This is nothing but fine spectrum, as you all know. This is fine spectrum, and this is denoted by azimuthal quantum number, right? Magnetic quantum, right? It's the angular momentum quantum number, that is nothing but the L value. So this is nothing but the subshell. So this is S, this in the second orbit S and P, and here S, P and D. Fine. These are what? These are nothing but the orbits. These are nothing but the orbits we are talking about. These are nothing but the subshells. We are talking about the subshells here. Now we are talking about the orbitals. We are talking about the orbitals. Now this is what we are talking, right? The orbitals here, S, right? It has only one. Okay, right. Now the first S orbital has only one, whereas P orbital is having 3 orbitals. I will explain you that. Right, let us come back to this one. That's what he says. It is dependent upon L value. How it is dependent upon, we will work on that one. So we know for azimuthal quantum number, L value is what, right? So for azimuthal quantum number, L value, it's nothing but L is equal to 0, azimuthal quantum number for S. Now for S, just now I said it is nothing but 0. For P, L value is nothing but 1. We know that. So now let's come back to this one. It is dependent upon N value. Now for a given value of L, if L is equal to 0, this is what? For S orbital, L is equal to 0, which implies the formula of ML is nothing but 2L plus 1. Fine. Now what is the value of L here? 0. That is 2 into 0 plus 1. The answer is 1. So 2 times 0, 0. 0 plus 1 is 1. Now how many ML values we have? It's nothing but only 1. Right, of course, right, that is nothing but only one value we are having. Now let us go for the P orbital. For P orbital, just now I said, for P orbital, L is equal to 1. Now if you like to know how many ML values it is having, now we are going to the formula 2L plus 1, which is nothing but 2 into 1 plus 1, 2 ones 2, totally how many we have? We are having 3 values we have, right? ML values for P. Now if you think about S orbital, P orbital and D orbital, let me specify that clearly for you. Right, suppose if this is nothing but S and this is nothing but P and this is nothing but D, assume like that. So S orbital we are having only 1, so that's where ML is equal to 0, only one value. Okay, for P orbital, how many orbitals we are having? It's nothing but 3. The P is divided into 3. That's what he says. The P orbital here gets divided into 3 parts. The S orbital, wherever it might be in the first orbit, it might be in the second orbit, it might be 3 orbit, any NS, it might be first, it might be second, it might be third. It divides the ML value, it has only 1. It is nothing but 1 S orbital. Now for P, whatever it might be 2P or 3P, how many values it breaks out? ML values are totally 3. What are those? We will get to know. Now for D subshell, L is equal to 2, ML values are nothing but the formula 2L plus 1, which is nothing but L is equal to 2. 2 2's 1, it's totally 5. So how many ML values does D has? Totally 5. So 1, 2, 3, 4, 5. These are nothing but the orbitals. Now it is nothing but right. MD means it might be 3D. It might be 3D. Why? Because it might be 3D or 4D or 5D, whatever it might be. So how many it has? It has 5 values. So what are those values? We will come to know. So the values, obviously, yes, right. Here as it is having 3 values, what are those? It starts from, what is the L value here? 1. So we will be having -1, 0. Yeah, as I have discussed here, again I am repeating, for S orbital, it's L is equal to 0. Now how many ML values are there? How many ML values? How many are there? Let us check it out. 2 into 0 plus 1, it's nothing but 1. So how many are there? Only one value of ML for S orbital. You have to remember that, right? So we have only one ML value. What is that? It's nothing but, you have to remember, ML value is 0, right? It might be in the first orbit, right? In the first orbit, K orbit, we are having 1s. For that 1s, ML value is 0. In the same way, for L orbit, we are having S orbital, we call it as 2s, right? For that one, ML value is 0. In the same way, for M orbit, right, we are having 3s. For that also, ML value is 0. So, for in the first orbit also, we are having only one ML value, that is nothing but 0. In the second orbit also, we are having only one ML value, its value is 0 everywhere. Now, what's the shape of S orbital? Right, this is very important for us now. So, what's the shape of S orbital? Now, right, if you take x-axis, if you take y-axis, and if you take z-axis, right, now the shape, the S orbital is always spherical. Right, so it's nothing but spherical. The shape of S orbital is always spherical. It's nothing but it's oriented along all the x, y, z exactly in the center. This is how we denote diagrammatically the shape of S orbital. Now, if you talk about for P orbital, what's the L value? Just now I have discussed L is equal to 1. If you plug in the value in the formula 2L plus 1, L is equal to 1. 3 we are getting. So how many ML values are there for P orbital? It has 3 values. ML values, it has 3 values. Then what are those values? So you have to remember, it's nothing but -1, 0 and 1. These are the values of ML of P orbital. Let's go back to this one. In the L orbit, we are having 2P and it is having 3 values, 3 orbitals. So it is nothing but the first one, it is nothing but -1. Later on, it is 0. For the next one, it is +1. Right. In the same way, if you repeat, go for the M orbit where we are having 3P, right? We are having 3 orbitals there. For that also, -1, 0 and +1. This is for 2P and this is for 3P. Totally, here also we are having 3 values. Here also we are having 3 values. It continues. Right. Now, what about the shape of the P orbital? Shape of the P orbital, as we have already discussed, it is oriented along 3 different axes. So, the first P orbital, which we call it as Px, right. Later on, the other one we call it as Py, and the other one we call it as Pz. Right. Why do you call it as Px and Py and Pz? Why? Because, right, the maximum probability of finding the electron Here it is oriented along x-axis, right? In the same way, for the second one, it is oriented along the y-axis, and for the third one where we are having +1, it is oriented along with the z-axis. So for here, ml value is nothing but we can take it as -1. For this one, ml value, you can take it as 0, and for here, ml value, you can take it as +1. It may be varying, but these are the generally what we call. And what is the name of the shape of s orbital? If you check it out, it is looking like dumbbell. So it is nothing but, right, dumbbell. So this is the name of the shape. It's nothing but dumbbell shape, right? So this is how we'll be figuring out the shape of s orbital and different values of. Now let's go for the what are all the orbitals present in D here. Now for D orbital, L is equal to 2. Now if you plug in the formula, ML is equal to 2L plus 1, whereas L is equal to 2. If I substitute in a formula, we are getting 5 values. What are those 5 values? 5 values is nothing but -2, -1, 0, +1 and +2. Right. How did you get that? Why? Because, right, it is clearly said in the magnetic quantum number that m value takes from -L2 and so on till +L values. This is the value taken up by ML values. Now means it is taking both negative values, it is taking 0, and it is also taking positive values. So it depends upon the L value from where it starts. Here L value is nothing but 2, right? Therefore it has to start from -2, -1, 0, +1 and +2. Why? Because it is saying that it has to start at -L. What is the value of L here? 2. Therefore -2, -1, 0, +1 and a +2. Now if you check it out, the same thing in the spectrum, right, emission spectrum. In the K orbit we don't have D value, therefore just ignore it. In the L second orbit L, we have only 2s and 2p, we don't have D there. Now the D orbital starts from the third orbit, whereas n is equal to 3, 3s, 3p, 3d, it is starting from here. Now it is having 5 values, what are all we have mentioned there. All those 5 values, -2, -1, 0, +1 and +1 and +2, we are taking from the 3D orbitals. It goes on for 4D, 5D and so on. For all the D, we will be having 5 ml values. Now if you talk about how they are oriented, yes, they are having 5 values of ml, but how they are oriented, along which axis they are oriented. Of course we are having x-axis, y-axis and z-axis. Of course we are talking about the D orbital, along which axis it is oriented means we come to the shapes of the D orbital. If you are talking about dxy, I have drawn x-axis and y-axis, just I have ignored z-axis just for the sake of diagrammatic purpose. Right, so now it is oriented in between the x and y axis. X and y axis it is oriented. How many dumbbells are there? 2 dumbbells are there, double dumbbell. So how many dumbbells are there? 2 dumbbells are there. Therefore, shape of D orbital we call it as double dumbbell. Alright, now let's get back to the next one. Here it is dxy, the ml value is -2, whereas if you go for dyz, right, I have drawn y-axis and z-axis, just I have ignored x-axis just for the sake of diagrammatic purpose. Now the orbitals are oriented, or the electrons are oriented in between y and z-axis. Right, in the same way, this is the xz. Now the electrons are oriented in between the x and z axis, Right, now whereas the fourth orbital where ml value is +1, here we are going ml value with -2, -1, 0 and +1 and +2. Here the next is nothing but x square, y square. In the D orbital, x square and y square. Here x and y axis I have taken. Now the electrons are oriented on the x and y axis. That's why, see, we didn't draw the lines there. It's on the axis there. Right. In the same way, if you go for the z square, it is nothing but it's the electrons are oriented, or the orbital is oriented on the z axis, whereas we are having x and y, we are ignoring there. So this is the diagrammatical representation of D orbital, saying that the values are taken from -L to +L, and the shape of that one is nothing but double. Yeah, let's come back to one of the important topics of magnetic quantum number is nothing but the degenerate orbitals. So what are these degenerate orbitals? Orbitals having same energy are called as degenerate orbitals. Orbitals having same energy are called degenerate orbitals. Orbitals having same energy are called degenerate. Why these orbitals are having same energy? That's the main reason. You have to remember that let's consider the orbits. This is the nucleus, first orbit, second orbit, third orbit, and so on. We know that as long as the electron is present in the same orbit, right, it has constant fixed energy. But when it jumps to the other orbit, the energy changes. It might be right excited state or ground state, but as long as it is in the same state, its energy is constant. That's what we need. We know. Now let us come to the second orbit here. Right, we know as S is present in the second orbit, it is 2s, and as P is present in the second orbit, we call it as 2p. In that one, as we already discussed, it is having three orbitals, px, py, and pz. Right, now in the L shell, that is what second one, L shell, right, this is nothing but 2px, 2py, and 2pz. All the three are present in the same L shell. Right, as long as these electrons, electron and electron is present in this 2px or 2py or 2pz, they all electrons are present at same L shell. Right, so as all the three electrons are present and all the three orbitals are present at the same L shell, all these three can be considered as a degenerate. In the same way, now let's go for the third orbit. In the third orbit, again we are having P, but as they are present in the P orbit, the third orbit, we call it as 3px, 3py, 3pz. Now the electron may be present here or here or here, wherever it might be. All the three electrons will be having same energy, or all the three orbitals, 3px, 3py, 3pz. These three will be having the same energy. Therefore, 3px, 3py, 3pz, we can call it as three generator. But one thing is clear, right? We can't compare 2px and 3px. Why? Because they are having separate, and when their relation is in between, no, they are not there. Only this set is degenerate. This set is degenerate. Means P orbital, right, all the three, px, py, pz are nothing but degenerate orbitals. Now, if you go for d orbital, we know all the five present there are the degenerate orbitals. So, in d orbital, how many degenerate orbitals are there? 5 degenerate orbitals are there. In p orbital, how many degenerate orbitals are there? 3 degenerate orbitals. The reason is, why? Because they are present in the same concept of magnetic quantum number is how many number of electrons are present in each subshell. Right, we are given a formula. Now let's get back. Maximum number of electrons in every subshell is twice the number of orbitals it has. We have to remember that one. How many number of electrons are there? Let me go with an example. Now let's go for the name of the subshell. Let us go for the S. Okay, we know the L value is nothing but 0. Okay, now let's plug in L is equal to 0 here. The number of orbitals it has is nothing but only 1. Okay, now if you multiply that 2 into 2L plus 1, we got it as 1. So number of electrons in the S orbital is 2. Let us go for this one. Now let us pick any S orbital. Yes, right. In this S orbital, maximum number of electrons can be accommodated is only 2. Why? Because it has only one orbital with the help of the formula 2L plus 1. Now let's get back to the P orbital. We know L is equal to 1. If you plug into that one, 2 into 1 plus 1, which is nothing but 3. Okay, now the same L value if you plug in here, that is 2, right, it's nothing but 3, right, 2 into 2L plus 1, 2 into 2L plus 1, we got it as 3, so totally how many electrons can be accommodated? Maximum number of electrons is 6. Let us check it out. So if you take, this is 2px, 2py and 2pz, we can accommodate maximum 2, maximum 2, maximum 2. Totally how many can be accommodated in the p orbital? It is 6, whether it might be in 3p, in 3p or 2p, whatever it might be, the maximum number of electrons can be accommodated is 6. In the same way, spt with L is equal to 2, here it is 5, and the double of that one is 10. You have to remember. In the same way, sptf, L value is 3. If you plug in 2 into 3 plus 1, it's nothing but 7. Now the double of that one, that is why, because 2 into 2L plus 1 is the formula. So 2 into, just now we got it as 7, totally 14. So the two main formulas, if the subshell, if you know the name, if you know the azimuthal quantum number of orbitals is given by the formula 2L plus 1, and the maximum number of electrons present in that orbital can be given by the formula 2 into 2L plus 1. The relation is double of number of orbitals it has. Why? Because in each orbital 2 electrons can sit. There is nothing but the end of magnetic quantum number with all the information. In this channel, I have been placing both math and science videos.